let capital S be the following surface. So let S be the graph of g of x comma y equals 3 plus sine of x plus sine of 2y for 0 less than or equal to x less than or equal to pi over 2 and 0 less than or equal to y less than or equal to 2 pi, oriented upwards. Well, let's set up an integral. For the flux of the vector field, capital F arrow, sorry, that arrow is a little hard to see here, equals xyz, comma, x cubed y, comma, x plus z squared across S. That's usually the language used. So how much water is going across this surface S? To answer this, we are going to need an orientation, which is usually labeled with an N. So this will be either a plus or minus of, and we, let's say offline, already compute the take this function right here and take g sub x cross g sub y, and you should end up with negative cosine of x, comma, negative 2 cosine of 2y, comma, 1. And this will be all over, well, we need the magnitude of that vector, so root 1 plus cosine squared x plus 4 cosine squared of 2y. Now, do we take the plus or do we take the minus here? Don't assume anything just because of the word upwards. What we need to do is take a look. If we take the plus symbol, is the third component positive or negative? Well, so for upward, there's already a positive 1 there, so we take the plus sign. Had we cross product in a different order, maybe there would have been a negative number here, so then we would have had to take the minus sign there. So at least as written, for upward, we need an upward orientation. So for the upward orientation, we're going to use the plus sign here. Now we need the function that we're going to integrate. So that's what we have traditionally called lowercase f. That is vector field f dotted with n. So in this example, just to make things connect back to things we've seen, it should be f dotted with n. So this will be, well, f is, xyz, comma, x cubed y, comma, x plus z cubed, dotted with n, and n is here with the plus sign. So let's get the vector here in the numerator, negative cosine of x, comma, negative 2 cosine of 2y, comma, 1. And let's just stick the scalar here in the denominator, 1 plus cosine squared x plus 4 cosine squared 2y. Okay, if we clean this up, let's just perform the dot product alone, and that's it. So we'll keep the denominator as is, 1 plus cosine squared x plus 4 cosine squared 2y, and in the numerator, when you perform the dot product, we'll have negative xyz cosine of x minus 2x cubed y cosine of 2y plus, 1 times, so let's see, 1 times, oh, sorry, that shouldn't be a cube, that should be a square there. So 1 times x plus z squared. Okay, so then for the flux itself, so the flux that we're asked to compute is, writing it like this, it's first of all the double integral over s of f dot ds. Okay, that's just notation though. What does it really become is the double integral over s of, writing it like this, f dot n ds without an arrow. Okay, and then this, in this example, right, is, well, let's just write two integral signs kind of some distance away from each other for now. F dot n, we had computed, and we have this right here. So we're just going to really just take that here, and and copy paste this into right there. Scale that down a little bit. Then we need ds, and that's as usual. Yeah, so ds as always should be the magnitude of g sub x cross product g sub y, and we actually already computed that. It's right. It's sitting right here. It's hiding amongst things we've done. So it's root 1 plus cosine squared x plus 4 cosine squared 2y, and then d capital A, but we can write that as a dx dy, and x goes from 0 to pi over 2, and y goes from 0 to 2 pi. So maybe we should just highlight something from the past. I know there's a lot of new things to note, but what's underlined in blue, ds, turned into the radical thing, then dx dy. Let's also comment that, of course, here we can cancel out we can cancel out this with that, and we actually still do have a z here and there that needs to be replaced with this right up there. So if we write this out a little more cleanly, we'll have integral 0 to 2 pi, integral 0 to pi over 2, negative x, y, z gets replaced with 3 sine of x plus 2y times cosine of x, then minus 2x cubed y cosine of 2y, then plus x plus, and then z here again gets replaced with 3 plus sine of x plus sine of 2y, quantity squared. Oh yeah, we did already cancel this with that, and then we have here what's left is dx dy. So that, let's stop our integral right there. We finally have as our integrand only x's and y's. And now we'll just move on to another sample problem. Let's find the flux of the vector field, angle bracket z comma y comma x across the sphere x squared plus y squared plus z squared is equal to 49. Actually, earlier we had parametrized, so r of u comma v is equal to angle bracket 7 sine of u cosine of v comma 7 sine of u sine of v comma 7 cosine of u for u going between 0 and pi, for v going between 0 and 2 pi. So we're just borrowing the parameterization that we had earlier. If we work out the magnitude of the cross product of the partial derivatives, right, this will be useful for the ds part, but it actually shows up as well in the denominator of the n thing as well. Yeah, so this will end up being 49 equals 49 sine of u. And we had also worked out earlier that the outward orientation, so it should be this divided by that. Sorry, not, well, let's clarify. It should be this divided by that with an appropriate sign of either a plus sign or minus sign in front, but we had worked out that the orientation in this case should be sine of u cosine v, comma sine of u sine of v, comma cosine of u. Okay, that's stuff we had worked out earlier, just mentioning this so that we can save a little time on the problem. And then the lowercase f, the function that we're going to eventually need to integrate, should be the vector field dotted with the orientation. If we work that out here, yeah, so the vector field dotted with the orientation, we're going to end up with z times sine u cosine v plus y times sine u times sine of v plus x times cosine of u. Okay, that's, I mean, it is equal to this, but we should actually get everything written in terms of u's and v's. So the z here needs to get replaced with with this 7 cosine u, so we're really going to end up here with 7 sine u, and then now we'll insert the cosine u, cosine of v, plus there's a y here that needs to get replaced with 7 sine u sine v, so we can write this middle term now instead as 7 times sine squared u times sine squared v, plus, and then this x needs to get replaced with 7 sine u cosine v, so then x cosine of u can be rewritten as 7 sine u cosine u cosine v. Then the flux of the vector field across the surface S is double integral over S of f dot n ds, which ends up equaling integral, let's leave a little space here, so we'll take the lowercase f, which is this thingy right there, and we're just going to copy paste this right down there. Okay, and then we need to take that, and then the ds right here needs to get replaced, but ds should be this 49 sine u times du dv. So this should be 49 sine u du dv. So I'll just underline in blue that part's the same as before. Okay, so yeah, this is the ds part. Yeah. Let's also put bounds on the integral, since the du is the inner integral. It goes from 0 to pi here, and then the outer integral is v from 0 to 2 pi. We'll just mention okay, we're really done with what wanted to do with the question right now, but let's just maybe make some mention that if you distributed 49 and there's a 7 on each of these terms and so on, so skipping quite a number of details, but this is an integral that you could work out some details for. I'll just mention that this ends up being 7 cubed times the integral 0 to 2 pi, integral 0 to pi of 2 sine squared u cosine v plus sine cubed u sine squared u. That seems a little odd. We'll just leave it like that. Du dv. And then skipping quite a bit more work, this ends up being 7 cubed times 4 pi over 3. I wouldn't worry about all of those things right now. Let's just say that the key step was to get to right here to set this up as an iterated integral. The comment I want to make, just the note, is that we're going to revisit this problem and do it in a much easier way. We'll revisit and see this done in an easier way. We'll be making use of a theorem to do so.